Hi, I'm Oliver Hope, and I'm going to be talking to you about our recent work, GDDR, or in full, Graph Neural Network-based Data-Driven Routing. Okay, so first of all, I'm going to start off with a little bit of context. Recently, deep reinforcement learning techniques have gained a lot of traction in the systems research space. This has commonly been to perform work such as optimizing systems in different ways. And the reason that deep reinforcement learning is such a good match here is that many such problems are both dynamic and combinatorial in nature. Now, deep reinforcement learning agents work by using neural networks to make decisions. Recently, there has been a lot of new work using graph neural networks, which are a way to perform deep learning on graph-structured data. Why is this exciting? Well, first of all, many systems can be modeled as graphs, an obvious example being computer networks, which provide a very natural use case. However, they also have other benefits, such as the control they give you over the relationships in the data that the neural network is and isn't allowed to take advantage of. But most importantly for us, they can help us generalize agents across different graphs, and this is what we take advantage of in GDDR. Now, how does data-driven routing fit into all of this? Well, there was some work published a few years ago called Learning to Route with DeepRL, which explored this very use case. Specifically, it explored intra-domain routing, with the aim being that of minimizing link congestion across the network at any one time. This method used a simple multi-layer perceptron-based deep reinforcement learning agent to show that this can be done successfully by learning over generated histories of traffic matrices. And so now we come to where our work fits in. Why use GNNs to solve this problem? Well, simply put, this seemed like a perfect example of something that could be improved with GNNs. The problem of using MLPs in the previous work was that once that the agent is trained, it will only work on one graph or network. What if we want to use the agent that we've just trained on a different network? Or what if we want to continue using the same agent on the same network, but now a node is down, or we've added a new node? We can't. The reason is that the current solution cannot generalize. We need some structure that can distill the problem, irrespective of the exact shape of the network being used. In the same way as we wouldn't approach the general idea of routing differently for every possible network graph. Hence, we decided to improve on the previous work by using GNNs combined with reinforcement learning to generalize to different network topologies. Now, let's take a look at the structure of the learning environment. So how the problem works is that the agent is given a state, which is a traffic history, and its task is to produce a good routing for the next time step. Then a reward for the agent is calculated by comparing its routing to the optimal achievable routing, which we calculate using a linear solver. What we actually compare is the congestion of the network under the routing and traffic in a time step. While we wrote the environment from scratch ourselves, most of the ideas were taken from the prior work. The actual new ideas present here are in the policy, which is where we added our graph neural network, and the soft-min translation, which is our custom algorithm that transforms weights on the edges of the graph to a routing strategy. Now for some quick detail on the policy that we decided to use. We used an encode process decode style policy built using the GraphNets library, and so it followed the GNN model which that library uses, where edges, nodes, and global state are processed separately. For the inputs, at the start we place the traffic history onto the nodes of the graph. We then run our model and retrieve the weights from the edges at the end. We also created an iterative version due to constraints in the variability of input sizes in most learning frameworks. In this version, the model is run once for each edge, with the edge input state used to indicate which edge we are running for, and the global output state is used to retrieve the edge weights one by one. Okay, so now let's have a look at how this method performed. So there are two graphs here, and the first on the left is a comparison between the MLP model, which is the previous work, and the GNN one, which is ours. What you're actually seeing is a single learning curve that is representative of the training for a static graph. We found that the GNN model tended to outperform the MLP one and would achieve this performance in fewer time steps. The second graph is one to actually demonstrate generalization. On this graph, a shorter bar is better, and the takeaway here is that an iterative method performs better, but that both policies can generalize and performed at least as well as the dotted line, which is shortest path routing used as a baseline for comparison. So to wrap up, this work shows that GNNs can be combined with deep reinforcement learning and do generalize when applied to systems. We've also provided policies for intradomain traffic engineering, which can generalize to different network topologies, and we've written an environment which can be used for further experimentation on this particular example. Furthermore, there is some future work that I think our work naturally leads to. So the combination of deep reinforcement learning and GNNs seems to be very powerful and should definitely be explored further in different contexts. In the case of our data-driven routing work, devising a better transformation from edge weights to routing strategies, I think, could have provided better performance and should be explored. But more generally, I think that although this work is interesting, it is still fairly synthetic and proof of concept, so it would be useful to try translating it into real-world systems for real-world experimentation. Thank you.